ideal gas law is a good approximation of the behavior of an ideal gas under a variety of conditions. Hi, this is Mr. B. In this video, I'll explain how to calculate the pressure, the volume, the moles, and the temperature of an ideal gas under a variety of conditions. Let's begin with the ideal gas equation, where pressure times volume is equal to moles times a universal gas constant, R, times the Kelvin temperature of it. Remember, the ideal gas law only explains the behavior of a hypothetical or ideal gas. However, the approximations are close enough to be related to real gases as well. When using the equation, the pressure is given in units of atmospheres. The volume must be in units of liters. N represents moles. The T must be in degrees Kelvin, and R, which is the universal gas constant, is calculated as follows. The universal gas constant R is calculated based on STP conditions, where at STP the pressure is 1 atmosphere and the temperature is 273 K. And of course, at STP, 1 mole of any gas occupies 22.4 liters, or 1 atm times 22.4 liters divided by 1 mole times 273 K will equal 0.0821. Atmospheres times liters divided by moles times K. The units of the universal gas constant will allow easy cancellation of units during a gas law calculation. Now let's apply the ideal gas equation to an actual practice problem. Consider the following. Calculate the pressure in atmospheres exerted by 1.82 moles of sulfur hexafluoride gas in a steel vessel with a volume of 5,430 milliliters at 69.5 degrees Celsius. The first step in answering this practice problem is to write down what is given. In this simple problem, we're seeking the pressure of sulfur hexafluoride, and we're given a volume of 5,430 milliliters, or cm cubed, a temperature of 69.5 degrees Celsius, and the moles of the gas will equal 1.82 moles. Now that the information from the practice problem has been gleaned, we should write the ideal gas equation, where PV is equal to nRT. And since the practice problem is asking for the pressure of sulfur hexafluoride, we may rearrange the ideal gas equation as follows, where P is equal to nRT divided by V. And in this simple calculation, we obviously divide it through by V to isolate the P. Now simply insert the data into the rearranged equation, where P is equal to 1.82 moles times the universal gas constant, 0.0821 atm liters divided by mole K, times the temperature, 69.5 degrees C. However, remember, when performing any gas law calculation, never use Celsius. When performing gas law calculations, always convert the Celsius temperature to Kelvin. To do so, simply add 273. So in this case, the T will be 69.5 plus 273, which will generate our Kelvin temperature. And of course, divide by the volume. However, the volume is given in milliliters. To convert milliliters to liters, divide by 1,000. So we're dividing by 5,430 mLs, which is divided by 1,000 mLs per liter, which may now be rewritten as follows. 1.82 times 0.0821 times 342.5, which is 69.5 plus 273, which represents our temperature, divided by 5.430 liters, which is 5,430 milliliters divided by 1,000 milliliters per liter. Remember also that during the previous calculations, the units will cancel, where moles will cancel, liters will cancel, milliliters cancels, and Kelvin will cancel, which leaves us with units of ATM. So the final answer will be 9.42 atmospheres. Okay, now let's perform a volume calculation. Consider the following practice problem. Calculate the volume in liters occupied by 2.12 moles of nitric oxide, NO, at 6.54 atmospheres and 76 degrees Celsius. In this problem, we're seeking the volume of nitric oxide, or NO. We're given a pressure of 6.54 atmospheres, and the moles will be 2.12 mole. And the temperature is given in degrees Celsius. However, remember, you may not perform gas law calculations using Celsius temperatures. Therefore, the Celsius must be converted to K. So the T will be 349 K. And of course, R, the universal gas constant, will be 0.0821 atmospheres times liters divided by moles times K. Now using the equation, solve for V, where V will equal nRT divided by P. And of course, insert the data. This will yield the following, where V is equal to 2.12 times 0.0821 times 349 divided by 6.54. And notice in this case I omitted the units because obviously the units will cancel and the final unit will be L. At any rate, the volume will be 9.2 liters. The ideal gas equation may also be manipulated to determine the density of a gas. Consider the following practice problem. Calculate the density of ammonia in grams per liter at 752 millimeters of mercury and 55 degrees Celsius. This practice problem may be easily solved by rearranging the ideal gas equation first, where PV is equal to nRT. And of course, N represents the moles, which may be rewritten as mass over molar mass. This will yield the following. PV is equal to mass over molar mass times RT. Further rearranging the equation, we generate the following, where mass over molar mass is equal to PV over RT. And since density is equal to the mass over volume, dividing through by V and multiplying through by molar mass will yield the following. Mass over volume is equal to density, which is also equal to the pressure times the molar mass divided by RT. Now simply insert the values, where the value for pressure was given at 752 millimeters of mercury. But millimeters of mercury may not be used in an ideal gas law calculation. So we must convert the millimeters of mercury to ATM. To do so, simply divide through by the conversion factor, 760 millimeters of mercury per ATM. The molar mass will be 17 grams per mole, which represents the molar mass of ammonia. And of course, the R will be 0.0821 atmospheres times liters divided by moles times K. And of course, the temperature, which was given in degrees C, must be converted to K by adding to the 55 to 73, which now converts the Celsius temperature to Kelvin. This will yield the following, where D is equal to 0.989 times 17 divided by 0.0821 times 328, which will equal 0.625 grams per liter. The units canceled in this step, where millimeters of mercury canceled, the ATMs canceled, the Kelvin canceled, and of course the moles canceled, which left us with the following units: grams per liter. The ideal gas equation may also be used to determine the molar mass of a gas. Consider the following practice problem. At STP, 0.28 liters of a gas weighs 0.400 grams. Calculate the molar mass of the gas. To solve this practice problem, remember that STP conditions are 1 atm and 273 K. The mass in the practice problem was given as 0.400 G and the volume was 0.28 liters. Now we turn to the ideal gas equation, where PV is equal to nRT, which may also be written as PV is equal to mass over molar mass times RT. Rearrange the equation will yield the following, where mass over molar mass is equal to PV divided by RT. Clearly, to isolate mass divided by molar mass, we divide it through by RT. Now we multiply RT times mass and molar mass times PV. This will yield the following equality. Mass times RT is equal to PV times molar mass. And of course, to isolate molar mass, we divide through by PV, which will yield the following equation. Molar mass is equal to mass times RT divided by PV. And now we simply insert the values, where molar mass is equal to 0.400 times 0.0821 times 273 divided by 1 times 0.280. And this will yield a molar mass of 32.02 grams per mole. Notice that during my calculation, no units were written. However, feel free to repeat this practice problem, write it into units, and prove that the units do actually cancel.